4. Daily examples of uniform circular motion. Let's take a look at some common examples of applications of centripetal force. A. Cars making turns on the level road. When a car makes turns on a level road, the friction that points towards the center of the path provides the necessary centripetal force. For the same speed, it requires a larger centripetal force mv²/r to turn around a corner of a smaller radius safely. When the road is wet, or when the speed of the car is too high, the road cannot provide enough friction for the centripetal force, so the car cannot turn in such a small radius, and the car will skid outwards. After it skids outwards, R increases, and hence the required centripetal force mv²/r decreases, and then the friction may be large enough to provide a new and smaller centripetal force, and the car does not skid any further. The friction airs on the car may be reduced to half on rainy days, and hence the maximum safety speed to turn around corner is reduced by about 30%. But why? In example 5, part B, the friction is reduced by half. The limiting speed to turn around the corner changes from 13.2 to 9.35 meters per second, which is 70% of that 13.2, and that 70% equals 1/√2. But why? B. Making turns on bent roads. Many corners, especially those of flyovers, are bented, which means one side is higher than the other. When the car turns on the bent road, the normal reaction acting on the car may also help. The horizontal component of the normal reaction points to the center of the path and provides the required centripetal force. The vertical component of normal reaction balances the weight. Thus, tangent theta equals v²/gr, which is the equation to find an ideal banking angle. However, you cannot apply the equation directly, but you have to derive the equation in examination. In example 6, you may see how we may apply the equation to find the banking angle. So an ideal banking angle corresponds to the single speed of the car to turn around the corner. What if the car is a bit faster or slower? Well, when it is a bit faster, it may skid off as there is not enough supply of centripetal force. However, it does not skid so easily because friction prevents it from skidding too easily. The car may skid if it is really so fast that the sum of horizontal components of friction and normal reaction cannot provide enough centripetal force, and therefore n sine theta plus f cosine theta is smaller than mv²/r. Similarly, friction also allows the car to run slowly around a corner of a banked road, as in figure 9.2n. Note that the frictions points to different directions, depending on whether the car is too fast or too slow. Therefore, the car may turn around the corner of a banked road safely if its speed is within the range of speed between the highest possible and the lowest possible speeds. Example 7 illustrates how friction and normal reaction together provides the required centripetal force. In part A and B, the direction of friction may tell us that the car is traveling a bit too fast, as the friction points radially inwards. In part D, the direction of friction may tell us that the car is traveling a bit too slow, as the friction points radially outwards. C. Aeroplanes making turns. Due to the shape of the wings, a flying aeroplane experiences uplifting force from air. In order to make a turn horizontally, it should fly with a tilting angle. In this way, the horizontal component of the uplifting force may provide the required centripetal force. And of course, the tilting angle depends on the speed of the aeroplane. So what will happen if the angle is a bit smaller or bigger? Can the plane keep its track along the circular path? In example 8, you may find the answers of the above questions of what would happen when the tilting angle and the speed do not match. Read the answer of part B carefully. D. The rotor in the amusement park. Rotor is an interesting ride in an amusement park. Take a look of the video first. At the beginning, the people enter the cylinder and lean on the wall. The rotor then rotates at high speed. And lastly, the floor is lowered, but the people remain stuck on the wall. At the time when the people perform circular motion, the normal reaction from the rotor wall on the back of the people provides the necessary centripetal force, and therefore normal reaction N equals mv² over r. In the vertical direction, the weight is balanced by the friction, which gives F equals mg. The friction F is in fact directly proportional to the normal reaction N, given by mu N, where mu is a constant. Hence, normal reaction N equals mg over mu, while normal reaction should also provide the necessary centripetal force. So the speed must be high enough so that N is large enough, which results in large enough friction mu N to balance the weight mg. In the rotor, there are people of different masses and heights. Do they need different minimum speed to stuck onto the wall? A washing machine also makes use of centripetal force to dry clothes. When the drum spins, the clothes experience centripetal force from the reaction of the inner wall, while the water droplets may fall through the holes and leave the drum tangentially. Example 9. Rotor ride. If, when the rotor rotates and people are stuck to the wall, the rotor rotates a bit slower, what would happen? What will happen if the rotor rotates a bit faster then? Example 9 may give you the answers of these questions. Read the last two parts carefully. Example link 2 investigates the action of friction for the circular motion of a mass on a turntable closely. In part A, a mass rotates with a minimum speed, and the friction on the mass directs outwards. In part B, the mass rotates with a maximum speed, and so the friction directs inwards. The two equations of motion allow you to find the maximum and minimum speed to keep the mass on the same circular path. The case is similar to the case when a car turns around a corner on a bent road, but a bit simpler. Of course, there can be many examples of applications of centripetal force, and yet the above 4 examples should be enough to demonstrate how to formulate the equations of motion in different cases. Just remember to find the net force, which should point towards the center, and that net force provides the necessary centripetal force. Do check point 5 on the next page, please.